Well, good morning, and today we're looking at the yaw control of a drone. And if you look at our little drone here, this is like the drone that we're flying, and the yaw control works like this, and we're going to do a yawing motion of that form there in hover. Now the drone itself has got two clockwise rotating and two anti-clockwise rotating propellers. So if you slow these two down and speed these up, you'll get a yawing motion. And that's the basic thinking behind the design or the control really of the drone in yaw. So let's have a look at now how it works. Here's a little drone, two going round clockwise, two going round anti-clockwise. If we slow these two up, then there's less torque from these, more torque from these, and so it's going to start to yaw in a certain direction. Now, the mathematical modelling for this is quite straightforward. It's more or less sitting in space because you're just hovering, there's very little friction. So we can apply the equation that T equals I times the yaw acceleration. So that's going to be, we use yaw as the output of this, it's going to be yaw double dot, which gives us a transfer function between yaw and the torque developed by the motors as just simply 1 over s squared. And then we've got the motors themselves, and we've got the motors in here, which have to speed up and slow down. And these can be measured by k over s plus a. And so the overall transfer function for the open loop system looks like this. Is the voltage applied here, the motor providing torque, then that giving us a yaw rate, integrate the yaw rate, and we get the yaw angle. And if we put this into a control system, the one we're implementing is a proportional plus derivative controller, so we've got some derivative control around this way and some proportional control around there. But this doesn't lend itself very well to root loci design, so we repose this problem in our standard form, K1S plus K2. We can then use root loci design methods now to get K1 and K2, and then we can go from this design back to this one, knowing simply that K1 is KD and K1 times K2 is KP. So this is then the underlying philosophy for our yaw control of the drone, and it comes down to a relatively straightforward root loci design from which we can use the angle and magnitude criteria now to actually figure out good values for K1 and K2 and therefore KP and KD. Once we've done our designs, we'll load the controllers onto the drone and see how it flies. And what we're going to do is we're going to look at a range of damping ratios for this and a range of performances for the drone, going from very lightly damped, where it's going to yaw something like that, to quite heavily damped, where it's going to yaw very slowly. So we look at a range of designs using these techniques. Right, so next thing we're going to do is now use the angle and magnitude criteria to work out some suitable controller for the system. We've actually modelled the system. We've worked out K as 1500 and the pole here at 400, so let's get minus 400, and we've got 1 over s squared here. So if we start plotting our root loci now up, well, before we really start that, we need to get our design conditions. So we need the complex conjugate roots now of this system to have certain, the dominant complex conjugate roots to have certain properties. So this is modelled by the s squared plus 2 zeta omega n s plus omega n squared equation. And we're going to choose omega n as 14.4 radians per second and damping of 0.7. And this gives me if I put these numbers in here, s squared plus 20s plus 207 equals 0. I've chosen these particular, just a bit of a cheap discipline, right? That gives me an s is minus 10 plus a minus 10j, so it makes it easy for me to plot it in my diagram. So this is my design point, where the complex root is at minus 10 plus minus 10j, which gives me a damping of 0.7, hardly an overshoot, and an actual frequency quite fast, 14.4 radians per second. So if we take this point now and this is the point now, so we plot now our Argon diagram. That's imaginary against real, and I've chosen scales of 10 on this particular diagram. And so this is the point here now, -10 plus 10j. And I've got 2 poles at the origin here, and I've got another pole all the way down here somewhere at -400, so that's going to be a really long way down there. So what we do now is we apply the angle criteria, so we draw lines from this point to the poles and eventually to the 0. We don't know where the 0 is yet, so we're going to have a 0 somewhere along here, which corresponds to the K2 value, and we can get this by using the angle criteria. So we've got alpha 1, which is the angle associated with the 0 that we don't know, and that's going to be beta 1 plus beta 2 plus beta 3. So beta 1 and beta 2, you can see if that's -10, that is going to be 135. We don't need the protractor. We don't need a protractor in this case. Well, if I did put it on this, it would be exactly 135 degrees. Because this is this is 45 there, isn't it? So that's a lucky angle for us. And this angle here, -400, this angle here is almost 0. It's about, I did work it out, it's about 1 degree. So the angle coming off the beta 1 and beta 2 are 135, and the beta 3 is about 1 degree. So if we solve this equation then, we get alpha coming out more or less at 90 degrees. It's about probably 89 or degrees, so it's quite close to 90. So we can draw this now in 90. So right at angle 90 is quite easy, isn't it? It's just going to go straight down here like this. So that means this angle here now, alpha 1, is 90 degrees, and that's going to occur here at exactly 10, because that's at 10, it's 90 degrees, so it's nice. I couldn't believe how simple this came out in the end. So that means now that K2 is at, this distance is K2, so that's at -10, so K2 is 10. So we get K2 as 10, and then when we got that, then we can go off now to apply the magnitude criteria. So again, we could take measurements of this, but because of the particular type of diagram we've got, where this is at -400, we can't take measurements of this. We'll have to do Pythagoras on it. We know that distance there, though, is 14.4, don't we? Because we figured that out anyway. So this one is 14.4. That's from there to there. We know from there to there will be exactly 10, don't we? And we could use Pythagoras on this bit because we know that we've got, that's 400 and that's 10. So we could use Pythagoras to get that one. It'll be the square root of 400 squared plus 10 squared. It's be about 400 and probably 412 or 408. So we can then stick those numbers into the magnitude criteria to get our K1. So the magnitude criteria, which is going to state now that 1500 times K1 times the 0 distance, which in this case would be 10, because from there to there is 10, divided by these distances would be 14.4 times 14.4. And if we call that distance there x, I haven't actually worked it out, but you can see will be around the 400 mark, won't it? Times x will equal to 1. And then we can solve this expression now for K1. And K1 comes out as 5.27. So, K1. So this is now 5.27. So, here's our final control now, 5.27 s plus 10. So in our actual design now, this is the, so we know now that KD will be the same as K1, so that'll be 5.27. And KP will be that times that, which will be 52.7. So when we come to implement this on the drone, we don't implement it in this format. We implement it in a slightly different format, but it's the same idea. So what we've got this time is we've got what's going on. That's a 1 over S there, a 1 over S there. That's the yaw, and that's the yaw rate. So in here we've got the KD, which is 5.27, and here we've got the K1, which is 52.7. So this is the design now. When we've got the drone, we enter these two numbers into the drone, and this is our overall flight control system for controlling the drone. And what we're hoping to do now is have a range of damping ratios, say all the way from say about 0.2 all the way up to damping of 0.4, 0.7, 1, even bigger than 1, say 1, 2 or something. So we'll have it very lightly damped all the way through to very heavily damped, and then look at the performance of the drone as it actually flies. And what I'm hoping to do, we'll see how it goes, is get the drone to come up, point towards you, and then do a little 1 radian turn. So 1 radian is about 57 degrees, so it's going to be sitting looking at you, and it's going to turn by 57 degrees, and we can see how well it does that task. So this is the design now of our yaw damper for the drone. It's a nice, clean, simple little model, very little friction in the air, so it's going to be, this part here is going to be reasonably accurate, and there's not much friction in this. And this is the only bit that's questionable, is the motor, but this is what I've figured out the motor to be, and then that gives us our controller designs then. And so this is an example now of using angular magnitude criteria to design a yaw controller for the drone. Right, this is the Mambo yaw control system. And if we have a look at the overall architecture of the simulation, there's a flight control system inside here, non-linear simulation here, state estimator here, some sensor dynamics and some visuals. The bit that we're interested in is the flight control system, and that's this block here. And it also has a visual input to help with the XY. Now the actual control systems itself on the drone consist of 6 PID control loops. There's a PID control loop on height, pitch, roll, X and Y. The one we're looking at today is the PID controller number 5 on yaw. It's actually a PD controller, and this is where the proportional gain goes in, and this is where the derivative gain goes in. The drone you can think of as having 4 motors and 4 main things you want to control: height, roll, pitch and yaw. And the motors are connected up through this decoupling matrix here, which essentially control the things. If we look at yaw, yaw will mean that motor 1 will go positive, motor 2 negative, motor 3 negative and motor 4 positive. So if we look at this motor 1 and 4, that's 1 and 4 go positive, 2 and 3 go negative. The reason for this is that the 1 and 4 are going around clockwise, and 2 and 3 go around anti-clockwise. So if these two go around clockwise and these two go anti-clockwise, if you speed these up, slow these down, there'll be a net yaw in this direction. We can use that force then to yaw the helicopter. Now, the actual control system itself, we have the simulation in Simulink, and we click on this box here to activate the actual flight control system. So we click on that block and we send it as a open as top model. This is how the particular software works. And then the software block comes up like this. We can then click on this block here, and we can change the controller gains in here. Once you've changed those gains, we can then go to here and we click on build and deploy. Build and deploy then downloads the software into the drone, and up comes this little window. We then send the power level up to 100% and click on the start button. Once you've clicked on the start button, it says preparing for takeoff, which means it's ready to go. And then just before the flight starts, it says mini drone flight started. Now we've got a stop button or a land button. So if we can stop the flight, we can press stop. If we want to land the drone, and we can press land if things are getting out of control. And at this point now, the drone will start to fly. And when the drone has completed its mission, it will land and say flight completed. Once the flight's been completed, we then click on this button here, MATLAB file, and it downloads the flight data into the MATLAB directory. Now it comes down as rsdata.mat, so if we double click on that, the data gets loaded in, and then we've got a little program here which plots some variables out, and it plots height against time, x and y against time, and yaw against time. And the one we're looking at in this particular case is a yaw, and we're putting a set point of 1 radian onto the yaw after 5 seconds. So typical response times now. This is a very lightly damped response from the quad because it's only got a gain of 0.0001, and we can see we've got this transient response here from the quad, and you can see there's quite a bit of motion in x and y, and around the point here where we did the change at 5 seconds, there's also a bit of disturbance in the height, although it isn't that bad. It's controlling to 0.1, which keeps it fairly level. It does eventually get control of x and y as well, but the yaw is very pure. You can see it's a very pure signal. It just does pure yaw, which is nice, and indicates maybe we should be able to get a good transfer function for that one. So right, here's our first design. It's the form of K1S plus K2, which is going to be finally implemented as a KP plus KDS, where this is KP, this is KD. We go for omega n is 14, damping of quite a low damping, 0.12. So we put these numbers into the standard second order system equation and come up with these following roots. We can then look for the 0, and we get the 0 in this particular case comes out as using the angle and magnitude criteria, and we can get the 0 comes out as 50. Then plot the root loci, and we read off the root loci the appropriate gain, and it comes out as 1. Notice these numbers here, minus 1.69, 17, 13.7, very close to these, and the omega n again very close to 14, and the damping at 0.12. So we more or less got this on the root loci. So that gives us a K1 as 1. So get K2 is 50, K1 is 1. Can then solve those for KP and KD. That's 50 and 1. So put the 50 in there and the 1 in there. Then run the simulation, and this is the response we get. Here's the code for plotting this root loci. And then we run put these numbers out to the real drone, and here's the drone response. And we can see now there's a very good correlation in terms of damping ratio, overshoots and undershoots, between the simulation and the real response. Whilst this flew, it generates, although it yaws very beautifully, it generates a lot of interaction on X and Y in particular. Right, here's our second design. Again, natural frequency of 14, this time a damping almost doubling to 0.256, still a very low damping here though. This gives us roots this time as using solving the equation s squared plus 2 zeta omega n s plus omega n squared as minus 3.5 plus or minus 13j, and so then we use the angle and magnitude criteria to locate the 0 k2. So using the angle and magnitude criteria, we located the 0 at 25 and then plotted the root loci, and from that we got the gain here when these roots matched up as minus 3.613, natural frequency of 14, damping of about 0.26. Then we found that we got K2 as 2. So that means that K1 is 50 and K1 is 2. So I've got a 2 in here and 50 in here. Here's the root loci code, and here is the transient response of the simulation, and here is the transient response of the drone for a 1 radian change in yaw at 5 seconds. So here we've doubled the damping ratio again to 0.54, so it's getting to a better sort of damping ratio, acceptable damping ratio. Omega n still at 14. Solve the equation s squared plus 2 zeta omega n s plus omega n squared equals 0 with these numbers in. Get the root system as minus 7.5 plus or minus 11.8j. So we then use the angle and magnitude criteria to locate the 0, K2. This time it comes as 12.5. Then plot the root loci and look for the gain. And the gain this time comes out as 4. This is to give the roots, more or less here, damping at this value 0.54 and the natural frequency as 14. So this looks like it's correct. Here's the root loci code that did that with the 0 at 12.5. We ran this simulation. This is the transient response, and this is the transient response of the drone under the same conditions with the same gains. The Kp in this case is 5 and the K1 is 4. Right, here's our next design. This time we're going for omega n 14, this time damping of 1, so it's going to be critically damped. The roots this time are going to be at minus 14, actually 2 at 14. So we can use the angle and magnitude criteria now to locate the 0, and it comes as 6.9. So with the 0 at 6.9, we put the number into here. So 6.9 is quite close to 7, should be 6.9. And then we run the MATLAB code, and we get a gain from this, from the root loci plot of K1 as 7. So K1 is 7 and K2 is about 7. So 7 7s 49, which I've rounded up to 50. So again, this time we've got a gain of 50 here and 7 here. This is giving us the critically damped case. And if we look at the simulation now, it is critically damped, and this is the drone running, and this gives very nice performance. Interestingly enough, with a critically damped design here on the drone,
its X and Y movements are much less, indicating that for a drone you really want it critically damped. This gives you a better overall performance than, say, going for a damping ratio of 0.6 or 0.7 as you might in a normal flight control system. Right, so this is our final design. Natural frequency of 14, but this time damping ratio very high, about 5. The root in this particular case is just a real root. You get a real and get two real roots, one which is quite a big real root and one which is quite a small real root, indicating that the performance there is going to be over damped, heavily damped. And in this particular case, we found the 0 came out as 1.25, and when we plotted the root loci, the gain came out as 40. I found it quite hard on the root loci plot to find this 40 because you very small movements here move this by quite a big number, but it was 40, and so we could then get the KD, which is K1, turns out to be 40, and then 40 times 1.25 comes to 50. So this time I've got 50 here and 40 here, and this has now made it heavily damped, and this is seen in the transient response. It's quite slow response here now. Remember the ones almost went straight up and across. It's a very, very slow response, and this was perfectly shown in the simulation or the running of the drone when the yaw response again was very slow. We can see that in the video of the drone. You can see it's slow moving. You can see it moving slowly, whereas when it's critically damped, you can hardly see it move at all. So here's my final design. This is the flight that the drone made in front of the telly as Everton scored against Liverpool, and it's quite interesting. I put a set point change in yaw up and down here at a couple of seconds, 5, 4 seconds, 7 seconds and 10 seconds. So it's, as you can see, this is the transient response of the real drone as it gets excited, as Everton score. Interesting enough, hasn't got really very big height. Changed the heights to about 0.7 of a meter to fly in front of the telly, and then this is the change in the Y. So you can see every time it made a change in yaw, it had about a 5 centimeter movement. Should have been down here, but it's a bit offset. But it wasn't quite. It's quite a small movement in Y, and similarly relatively small movement in X as well. So this is quite a stable response. This first part is as it gets up to height. The height control system I've made quite heavily damped, so it's a little bit slower than normal, but this gives you an idea of how the system performs when it's critically damped and how it affects the other variables as well.